Welcome to the Deep Dive, where we plunge into the cosmos, exploring the universe's most compelling questions and peeling back the layers of cosmic mysteries.
Great to be here.
Today, we're focusing on an exoplanet that has kept astronomers, well, on the edge of their seats for years, a truly intriguing world named GJ 1132b.
Yes, that one's caused quite a stir.
For a long time, the scientific community wrestled with a fundamental question about it. Does this rocky, Earth-like world actually possess an atmosphere?
Right, and the data was confusing, to say the least.
Exactly. Frustratingly contradictory for a significant period. So our deep dive today is all about how the incredible James Webb Space Telescope, the JWST, finally brought some clarity to this cosmic riddle.
A much-needed resolution.
We'll uncover the definitive answer about GJ 1132b, and crucially, what this means for our broader understanding of planets orbiting M-dwarf stars.
And those are the most common type of star out there, so it's a big deal.
Absolutely. Yeah. Smaller, cooler, dimmer than our sun. So this isn't just about one planet's fate. It's really about refining the very methods we use to find potentially habitable worlds.
Yeah, it shapes how we search for life beyond Earth. It's a significant story of, scientific perseverance and precision.
So let's first dive into the specifics of GJ 132b itself, because its characteristics are really key to this whole mystery.
Okay.
This is a rocky world, quite similar to Earth in some fundamental ways, with a radius and mass only slightly greater than our home planet.
Which makes it interesting right off the bat. An exo-Earth analog, sort of?
Exactly. That alone makes it a compelling target. But here's where it gets, well, really wild. Its orbit. It's incredibly unique, almost hard to believe.
Oh yeah, it's extreme.
GJ 132b hugs its host M-dwarf star at a mere 0.0153 astronomical units away.
Which is incredibly close. Like Mercury is way further out from our sun comparatively.
Way further, nearly 25 times closer than Mercury is to our sun. It's practically skimming the star's surface. Because of this extreme proximity, it completes an orbit in a blistering 1.6 Earth days.
A year there is less than 2 days long. Just imagine.
Crazy. And for those wondering, it's located about 41 light years away.
So, cosmically speaking, a next-door neighbor. Close enough for our best telescopes to get a good look.
Right. Now, intuitively, you might think that given such intense proximity, there's just no way this planet could possibly hold on to an atmosphere.
Yeah, the stellar radiation, the heat, it should just strip it bare.
That's what you'd think. Yet, fascinatingly, some theoretical models actually suggested that even worlds so incredibly near to M-dwarfs might be able to retain an atmosphere.
And that created a real debate, didn't it? A planet that seems like it shouldn't have air, but maybe, just maybe it could.
Exactly, a proper scientific puzzle.
And that's the crux of the tension, really. Because on one hand, these M-dwarf stars, while super common, are also incredibly active, especially when they're young.
Right. They're not exactly calm neighbors.
Not at all. They're known for emitting strong, high-energy radiation and frequent, powerful flares.
So bursts of energy that could really wreak havoc on a nearby planet.
Precisely. Those characteristics are exactly what make retaining an atmosphere an immense challenge for any planet orbiting close by. Those stellar winds and sudden outbursts can just blast a planet's gaseous envelope right off into space.
A really harsh environment, then.
Extremely. It's why astronomers developed this concept called the cosmic shoreline.
Okay, what's that exactly?
Think of it as an invisible line, a kind of point of no return, if you will, where a planet simply can't hold on to an atmosphere.
Why not?
Because the intensity of its star's radiation, what we call stellar irradiation, combined with the planet's own size and gravity, just makes it impossible.
I see. So beyond this shoreline.
The odds of an atmosphere surviving are incredibly slim, almost zero. It's a critical boundary in exoplanet science.
And the question of GJ 1132b's atmosphere matters so much because it sits right near that potential shoreline.
Exactly. It's a crucial data point for understanding habitability, or, the lack of it, around these M-dwarf stars.
Which are, again, the most common stars in the galaxy.
Yeah, about 3/4 of them.
Mm-hmm.
So cracking this code for M-dwarf planets is vital for understanding where life might or might not exist. It helps us draw those boundaries more clearly.
Right. So we had this intriguing planet, GJ 1132b, this huge question mark over its atmosphere, and then the James Webb Space Telescope enters the picture.
Our most powerful tool for looking at exoplanet atmospheres.
And this new study we're talking about directly engages with that debate, building on earlier work. because before this, previous JWST observations of two different planetary
That's
transits.
when the planet passes in front of its star from our view.
Right. Those produced, honestly, conflicting results. One data set indicated a water-rich atmosphere.
Which got everyone very excited, naturally. Water.
Incredibly exciting. But then another entirely separate observation suggested absolutely no atmosphere at all.
Total opposite. So a classic scientific dilemma.
Exactly. Two pieces of seemingly good evidence pointing in completely different directions. It just cried out for more data.
Definitely needed clarification.
So, given those conflicting results, the pressure was really on for this new study. How did these researchers finally untangle that knot?
Well, they went back to JWST, and they observed two additional transits of GJ 1132b.
Okay, so doubling down on the observations.
Precisely, with painstaking care. And after analyzing these two new data sets alongside the existing ones, really carefully incorporating all the available data, the definitive conclusion became, well, overwhelmingly clear.
And what was that conclusion?
The evidence now firmly supports that GJ 1132b is almost certainly airless.
Almost certainly airless. Okay.
Yeah. And that conclusion gets even stronger, more consistent, when you consider the three robust data sets that now point decisively to the same outcome, ignoring that first outlier.
Ah, so 3 out of 4, essentially.
Well, three consistent ones versus one that looked different. It's a powerful testament to the value of repeated, consistent observations in science.
Makes sense. Repeatability is key.
Absolutely.
Yeah.
And this is where the nuance comes in, because science is rarely absolutely black and white.
Always some wiggle room.
Sometimes. While the evidence overwhelmingly points to an airless world, the researchers found there's still a tiny, tiny bit of room in the data
For what?
for what they describe as a very low pressure, maybe around 1 millibar, steam atmosphere.
1 millibar. What does that mean in context? Earth's atmosphere is...
About 1,000 millibars at sea level. So
Yeah.
1 millbar is incredibly thin, almost a vacuum,
Yeah.
barely there at all.
Okay, so practically nothing.
Pretty much.
Yeah.
However, if we connect this to the bigger picture, the broader scientific consensus, most astronomers are quite confident that even that thin steam atmosphere isn't actually present.
Why not?
Well, again, it's extreme proximity to the star. Retaining even that thin steam layer would be incredibly difficult with the constant stellar bombardment.
Right, we keep coming back to that.
And crucially, previous JWST studies had already noted a seeming lack of water on GJ 132b. So finding steam now would be odd. So that fleeting possibility of a steam atmosphere, it essentially vanishes almost completely if you exclude that initial conflicting data set from the analysis.
The one that suggested water in the first place.
Exactly. The consensus is really strong when you look at the consistent data. Repeatable results, that's the goal.
So, if the latest data is so overwhelmingly clear now, what was going on with that initial observation? The one that suggested water. Was it just bad data, or...
That's the fascinating part, the detective work. It wasn't necessarily bad data, but it was misinterpreted because of something else happening.
Okay.
The authors went back and looked not just at the planet, but at the M-dwarf star itself during the time of that first anomalous transit observation.
Ah, looking at the star's behavior.
Exactly. And what they found was the breakthrough. There were more cool spots on the star's surface during that specific period.
Cool spots. Like sunspots on our sun.
Precisely. Areas of lower temperature, intense magnetic activity. The presence of these extra cool spots in the star during that first observation actually influenced the light filtering through, well, what they thought was the planet's atmosphere.
How did that work?
These spots can subtly alter the star's light spectrum as the planet passes in front. It created a signature in the data that mimicked the presence of an atmosphere, specifically one with water, when in reality, the planet was likely still airless.
Wow. So it was an effect from the star, not the planet, creating a kind of cosmic mirage.
That's a great way to put it, a cosmic mirage. It highlights just how complex this cosmic detective work really is. Even with our best tools like JWST, you have to account for the star's own variability.
Which leads to the next question, right? How do we avoid this happening again?
Exactly. And this raises an important point for future exoplanet research, which is crucial for refining our methods.
So we don't fall into similar traps.
Right. The authors propose a clever and robust solution, especially when studying stars that are known to be highly variable, like many M-dwarfs often are.
What's the solution?
They suggest using a leave-one-out approach for analyzing exoplanet datasets.
Leave one out. What does that mean?
In practice, it means you analyze your full set of data, say 4 observations. Then you repeat the analysis 3 more times, each time intentionally excluding one of the observations,
Okay. Why?
to see if the overall conclusion changes significantly when one piece is removed. If the main result holds true, even when you temporarily ignore one data set, it gives you much greater confidence in your findings.
Ah, I get it. It helps spot outliers or data affected by temporary weirdness, like those star spots.
Exactly. It's a powerful way to identify and account for potential outliers or subtle stellar activity, like having multiple witnesses. If the core story stays the same, even if one witness steps out for a moment, your story is much stronger.
That makes a lot of sense. Did they mention the specific instruments used?
They did. They used JWST's NIRSpec instrument, the near-infrared spectrograph, and they actually use it in 2 different modes. One with high resolution but a small data gap, and one with medium resolution.
Any difference in the results?
Interestingly, they noted that the overall data quality and noise levels were pretty comparable between the modes, which is good news. It means both are robust.
So practical advice for other astronomers, too.
Yes, they recommended maybe using medium resolution if you only have one transit to observe. But high resolution is perfectly fine, maybe even preferable if you have multiple transits you can combine. Crucial practical tips for maximizing telescope time.
So ultimately, this paper pretty clearly puts to rest the idea that GJ 1132b has an atmosphere, especially any sort of thick one.
Yes, it's a definitive answer to that long-standing puzzle that really had the community scratching its head.
But the importance, as you said, is really twofold here.
Hmm.
It not only solves the mystery of the specific planet, but also offers these refined methods, like the leave one out approach, to prevent similar confusion in future studies.
Absolutely. It's about improving the very toolkit we use to explore these distant worlds, ensuring we get clearer, more reliable answers going forward.
Getting better at reading the signs.
Exactly. And what truly stands out about this whole situation is how these findings connect back to that critical ongoing debate about M-dwarf habitability.
Right. Can planets around these common but active stars actually be habitable?
That's the billion-dollar question. And this new data point for GJ 1132b, particularly for a rocky planet in such a close orbit, firmly supports the idea that these types of planets can't reliably hold on to atmospheres under such intense conditions.
Adding weight to the no atmosphere side of the argument for planets this close in.
It really does. It contributes significantly to a growing body of evidence that helps us define that cosmic shoreline more accurately. Before, we had theories and models about atmospheric escape around active stars.
But this is real-world data.
Real-world JWST-level empirical data for a specific, well-characterized rocky planet. That's invaluable.
So this isn't just about one rocky world's maybe disappointing fate.
Not at all.
Yeah.
Even finding an airless world is a vital contribution to the whole field. Every new data point, even a null result like this, strengthens our predictive models. It allows astronomers to fine-tune their simulations for planet formation, to better understand the true resilience and escape mechanisms of atmospheres. And ultimately, it gets us much closer to identifying the specific ingredients, or the lack thereof, for potential life out there.
Like adding a crucial piece to this enormous cosmic puzzle.
That's a perfect analogy. A well-defined corner piece, maybe, helping us clarify the big picture of planetary evolution and habitability around the most common stars in the galaxy.
And what a journey it's been for this one planet. From puzzling, contradictory data sets to a clear, definitive answer.
Thanks to advanced telescopes and, just as importantly, rigorous scientific methods that even accounted for the star's own blemishes.
It really highlights that the takeaway for you listening is clear. Understanding that dynamic interplay between a star and its planets is absolutely key to deciphering the secrets of exoplanet atmospheres.
You can't just look at the planet in isolation.
Exactly. It's not just about finding a planet. It's about understanding its entire cosmic neighborhood, its environment. So, as we conclude this deep dive, the implications of these findings, they open up some truly profound questions, don't they?
They really do.
If even Earth-sized rocky worlds around these M-dwarfs struggle so much to hold onto an atmosphere when they're this close, what does this imply about the true boundaries of that cosmic shoreline for habitability?
Does it push the line further out? Make truly Earth-like worlds rarer?
Exactly. Does it mean finding potentially life-sustaining worlds is even rarer than we once thought? Does it push our search perhaps to different types of stars or different types of planets around M-dwarfs further out?
Or maybe redefine what habitable even means in those contexts.
Perhaps. It's a question that continues to drive the incredible work happening in exoplanet research.
Use is busy, that's for sure.
And it's certainly something for all of us to mull over. Keep an eye on new discoveries. The universe always has more surprises in store as we continue our quest for knowledge.
Always more to learn.